In this video, you're going to get an introduction to curve sketching. Chapter 3 is all about taking the different things that we've learned so far in order to create an accurate graph of a function without using a graphing calculator. So now we're going to take everything that we have learned from section 3.1 through 3.4 and kind of tie it all together and bring it into this curve sketching process. All right, so we're going to do this over 3 separate days. Here's day 1. So there are 4 general guidelines to follow in order to create a curve using the curve sketching process. So the first thing that we're going to do is called a pre-derivative analysis, and this is working with the original function that was provided to you. And there are 3 big things for you to look for. The first is the domain, and not necessarily what the actual domain is as an interval, but more specifically, are there domain restrictions, and if so, what are they? So you're going to focus on looking for holes, vertical asymptotes, and gaps in the graph. And honestly, gaps tend to only happen, in the most part, with piecewise functions, and we're not dealing with piecewise functions here, so we're really focusing on looking for holes and vertical asymptotes. Next, you want to be able to determine the range. Similar to with domain, we're not so much concerned with what's the biggest y value and the smallest y value, but more so, what's the end behavior of the graph, or are there any horizontal asymptotes? And then the next thing you want to look for are your x and y intercepts. Now, you should be able to find the y-intercept regardless of what kind of function it is. However, finding the x-intercepts, if it's a polynomial, you want to be able to do it by solving by factoring. And if you can't do it by solving by factoring, then it's probably not worth the time and effort to find the x-intercepts, because there will be lots of other things that you're going to find through the other steps that will help you to fill in where those x-intercepts are. Okay? The important thing with an x-intercept is to make sure that you look at the factored or reduced form to find it. And I'll point that out a little bit later. After you do a pre-derivative analysis with the original function, you're going to do a first derivative analysis. That is where you find your intervals of increase and decrease using a first derivative number line. And then you're also going to use the first derivative test to find your relative extrema, maxes and mins. And you're going to identify those as coordinate points. Then you're going to go through and do a second derivative analysis. You're going to determine intervals of concavity by doing a second derivative number line. And you're going to use that number line to identify any points of inflection. And again, since they're coordinate points, you want to go back and find the y values to make these actual points. So now you're going to have 3 different analyses completed. And you're going to have lots of information from those 3 different things. You're going to use that information to sketch the graph using all of the key features. So you want to start off by plotting all of the points and drawing in any asymptotes, both vertical and horizontal, depending on what you have. And keep in mind, a polynomial and some other functions won't have asymptotes involved. Then you're going to focus on concavity and where the function is increasing and decreasing to get the proper shape. All right, so let's talk about concavity and increase and decrease for a minute. So here I've drawn what a function will look like if it's concave up and if it's concave down. If you take the concave up sketch and cut it in half, you should be able to see that one side is increasing and one side is decreasing. The question is which is which? The increasing happens on the right-hand side. So there we go. Increasing on the right-hand side. So something that is concave up and increasing will start off with a very gradual increase and then quickly become a very steep increase. That means the left-hand side is decreasing. So anything that is concave up and decreasing will look like the left-hand side of this graph. We can do the same thing with the concave down. Cut it in half. The left-hand side here is increasing, and the right-hand side is decreasing. Okay, so we can use these pieces to try to figure out which way the graph should bend for the different intervals that we're looking at. Don't stress about this too much. We're going to be going over this in detail when we get to a full curve sketching problem in class tomorrow. All right, next up is domain. And like I said before, when you're focusing on domain, you want to focus on what are the restrictions. So the type of function you don't see written here is a polynomial, and that's because a polynomial doesn't have any domain restrictions. So we're going to focus on radicals and rationals. And when you're looking at a radical, you want to focus on the index, the n. If n is even, we have domain restrictions. Think of a square root. You can't find the square root of a negative number. That means if n is even, the domain would be something along the lines of the inside, in this case just plain old x, has to be greater than or equal to 0. Okay? So the radicand, or the expression inside, has to be greater than or equal to 0 if n is even. Okay? If n is odd, you could have any of the real numbers inside. Like a cube root. You can take the cube root of any number, a positive, a negative, or 0. Okay? If you wanted to write it as an interval, it would be negative infinity to infinity. Okay? But we're not going to be super strict on what notation you need to use. So if you want to use all real number symbol, or if you want to use interval notation, either one is fine. Okay, rationals. When you have a rational function, you need to focus on the denominator and make sure that the denominator does not equal 0. Okay, so again, we're focusing on denominator can't equal 0, but that could be one of two things. If the denominator is equal to 0 in the original, you can have either a whole or vertical asymptote. So the question is, how do you know which is which? And a whole happens when something is reducible. And a vertical asymptote happens when it's not reducible. So what do I mean by that? All right, let's take a quick look at an example. So let's take a look at the expression x plus 3 over x squared plus 3x. Oops, that should be a plus sign. There we go. Now, that reduces down because the denominator factors into x times x plus 3. So this is the same thing as 1 over x. Okay? Now, if I look at the 1 over x, the domain restriction there is x cannot be 0. That's a vertical asymptote. Okay? So there's a VA at x equals 0. But the original problem, I wasn't allowed to plug in x equals negative 3, because then I would get 0 over 0. That means that there is a whole at x equals negative 3. All right? So if the factor reduces out, that means that there was a whole at the x value that made that factor 0. If the denominator had a factor that doesn't disappear, that doesn't reduce out, that means you have a vertical asymptote. Okay? We'll take a closer look at wholes versus vertical asymptotes in a later example. All right, so some really helpful pre-derivative information. First thing we're going to talk about is polynomial end behavior. You focus on the degree being either even or odd, and the leading coefficient being positive or negative. So if it's even and positive, picture a parabola that opens up. It goes up, up. The negative makes it the exact opposite, down, down. If the degree is odd and it's positive, picture the basic cubic function. That goes down, up. And then if it's odd, negative, it's the exact opposite, up, down. Okay? Next, let's talk about intercepts. How do you find an x-intercept? Well, what you do there is you set it equal to y, or rather set y equal to 0, and then solve for x. So we're setting y equal to 0, and we're solving for x. All right, when you're doing rationals and radicals, that should be fairly straightforward to do. When you're doing a polynomial, though, sometimes it doesn't factor. So here's an important note to make. If the polynomial won't factor, then you can skip finding the x-intercepts. It won't be worth the effort to go through and find them because we're probably going to be able to naturally see the approximate x-intercepts based off the other information that we have. Okay? So I'm going to jot that note down. Alright, so again, if the polynomial doesn't factor, you can skip finding the x-intercepts. That means, however, that if it does factor, you are responsible for finding the x-intercepts by solving by factoring. Y-intercepts are a little bit easier. All you do is plug in x equals 0, and then you get an answer for y. Pretty straightforward. You should always be able to find the y-intercept. The exception would be if you add a rational and plugging in 0 makes it undefined, then you don't have a y-intercept. Okay? And the last thing that we're going to talk about as far as this slide is concerned is finding the end behavior for a rational. And that's really the quest to figure out, is there a horizontal asymptote? So this goes back to the idea of limits as x approaches either infinity or possibly negative infinity for a rational. We focus on the biggest degree on the top versus the biggest degree on the bottom. And here we have 3 separate cases. Okay? The first one, if m is bigger than n. So if the exponent on the top is bigger than the exponent on the bottom, that means your y is going to approach either positive or negative infinity. Okay, because it's top heavy. That means that there is no horizontal asymptote in this situation. And to figure out what the end behavior is, we would simplify down whatever ax to the m over bx to the n is, and then revert back to polynomial end behavior. The second case is if m is equal to n, and therefore the limit would be y is approaching a divided by b. And that's because you would have something like a x to the 5th over b x to the 5th. The x to the 5th would cross off. You're left with a over b, which is just a number. So that means you have an HA, or a horizontal asymptote, at y equals a divided by b. The last case that you could have is if m is less than n, so it's bottom heavy. That means that y would be approaching 0. And you have a horizontal asymptote at y is equal to 0. Alright, so that's all of our pre-derivative information. Now, I know you've heard a lot of talking about me. We haven't done any examples yet, so now we're going to go through 3 separate problems. Here we go. One of each type. We're going to do one polynomial, one rational, and one radical. So we're going to do just the pre-derivative analysis. That's the focus of this video. So, f of x is equal to 8x cubed plus 20x squared minus 2x minus 5. So let's start off with domain. Are there any domain restrictions on a polynomial? And the answer is no. There's nothing that makes this undefined. So you could say the domain is all real numbers, or you could say it's from negative infinity to infinity, or you could say just no restrictions. Any of those answers would be fine. I'm not going to be really specific about which format you have to write it in. Okay. Next, we want to focus on our range, or rather our end behavior. EB, end behavior. So in order to figure out end behavior, we focus on the leading term, which is the one with the biggest exponent. Keep in mind, it's not always written in order. But here we have a positive leading coefficient in an odd degree. That means our end behavior would be down, up. Okay? We don't need to know what the lowest y value is. We don't need to know what the highest y value is. We just need to know the end behavior to figure out our tails. Okay? So this is the range idea here. Okay, next up, y-intercept. If I plug in x equals 0 into this equation, I'm going to get negative 5. You should write this as a coordinate point, 0, negative 5. Okay, so that's a point that we would plot. And last but not least, x-intercept, which is usually the most work when it comes to a polynomial. So what we're going to want to do in order to do that x-intercept is we want to take the equation, set it equal to 0, and solve for x. And this will factor. So you're responsible for factoring. Since there are 4 terms, we're going to try factoring by grouping. The first 2 terms have 4x squared in common, and that leaves us with 2x plus 5. The second set have a negative 1 in common, and that also leaves us with 2x plus 5. So if I factor that down, I'm going to get 2x plus 5 times 4x squared minus 1. This is equal to 0, and we get 3 answers. We're going to get x equals negative 5 over 2. And then from the 4x squared minus 1, you can either do difference of squares or solve by square rooting. But you should end up with plus or minus 1/2 out of this. If you're not sure how, ask me in class tomorrow. So now our x-intercepts, there are 3. Negative 5 over 2, comma 0. Negative 1 over 2, comma 0. And 1/2, comma 0. And it's fine to use decimals here, because you're going to need to know the decimal approximation anyways in order to plot it accurately. So using decimals is okay. Just make sure that you don't do any rounding until you get to your final computation. So that's a pre-derivative analysis for a polynomial. Next is a pre-derivative analysis for a rational. And here, the most important work is figuring out your domain. That's going to take the most time. So, domain. We want to focus on getting this into the simplest form possible, which means we need to factor. So if we look up top, the top factors, like so. We're going to have x plus 1 and x plus 2. And the denominator, I can factor out a 2, and then I have x squared minus 1. And that's difference of squares, x plus 1, x minus 1. So this reduces down because they have x plus 1 in common on the top and the bottom. So this is x plus 2 over 2 times x minus 1. So that means that we had 2 domain restrictions. Back here we have 2 domain restrictions. X equals negative 1, x equals positive 1. So the domain is x cannot equal plus or minus 1. But we want to be able to identify which one's the whole and which one's the asymptote. Now, since the x plus 1's disappeared, that means x equals negative 1 is a whole. So x equals negative 1 is a whole. And x equals positive 1 is a vertical asymptote. Alright, whatever x value is still a domain restriction over here, that's your vertical asymptote. Okay? Now, to figure out the precise location of the whole as a coordinate point, and yes, you do need to know how to do this, we would take negative 1, plug it into the reduced form, so that would give us negative 1 plus 2 over 2 times negative 1 minus 1. That's 1 over negative 4, or negative 1/4. So the whole is at the point negative 1 comma negative 1/4. And again, we'll do this more when we get to the full curve sketching process in the next 2 days. Okay? So we've got a whole at x equals negative 1, a vertical asymptote at x equals 1. Next up, we want to think about our range. But more importantly, we want to focus on, are there any HAs? Any horizontal asymptotes? So we're going to look at the limit as x approaches infinity of the leading terms, x squared over 2x squared. And that will just be 1/2 because the degrees are the same. So we have an HA, horizontal asymptote, at y equals 1/2. And later on we'll talk about how do we know when, if at all, we cross the horizontal asymptote. We'll talk about that in 2 days. Alright, y-intercept. If I plug in x equals 0 into the original equation, I would get positive 2 up top, negative 2 on the bottom. That gives me negative 1. You could do the same thing with the simplified version, which is written in green, the x plus 2 over 2 times x minus 1, and get the same result. To get the x-intercept, you want to look at the finalized, simplified version. And you want to focus on the numerator being equal to 0. So in this case, it's just negative 2, 0. Okay? If I went back to the original and did the numerator equal to 0, I would also get x equals negative 1. But we know that there's a hole there, and if you look at the y value for the hole, it's not 0, so it's not an x-intercept. Okay? So again, x-intercepts only look at the reduced form, and you're focusing on the numerator being equal to 0 there to get an x-intercept. So that's a pre-derivative analysis for a rational. All right, we have one problem left. Sorry this is taking so long, but we're going to go through and look at a radical. All right, domain of a radical. This will have domain restrictions because there's an even index. This is the square root. So we need to figure out what our domain is. It is not all real numbers. So since it's an even index, we need to take the inside, the radicand, 4 minus x squared. And we need to say, okay, that's greater than or equal to 0 and solve. Right? If we pretended it just said equal to, then we would get positive 2 and negative 2. So we're going to put those on a number line. And now we're going to kind of test what works and what doesn't. But here's the thing. 4 minus x squared by itself would be a parabola, and we'd either shade above it and inside or below it and outside. So we really just need to test one number. We're going to test the number in the middle. We're going to test 0. If I plug 0 into this up here, I get 4 is bigger than or equal to 0, and that's true. So that means the numbers between negative 2 and 2 work, and the numbers outside do not. So our domain here is going to be brackets negative 2 to 2. And then as far as range is concerned, or rather end behavior of this graph, because radicals, generally speaking, don't have asymptotes, we're more concerned with end behavior. This is not something we really need to worry about because infinity and negative infinity are not a part of the domain. So we're just going to write none because no infinities in domain. Alright, y-intercept. If I plug 0 into the original equation, I get the square root of 4. The square root of 4 here is just positive 2. There's no negative 2 because there's no plus or minus written in front of the square root in the original problem. Since it's just y equals positive square root of, the answer for the y-intercept is just the positive square root of 4. Alright, x-intercept. If I set the square root equation equal to 0, I'm going to basically end up with 4 minus x squared is equal to 0. Well, that gives us plus or minus 2. So we're going to have 2 comma 0 and negative 2 comma 0. And yes, you need to write it as 2 separate coordinate points. Do not write plus or minus 2 comma 0. And the reason for that is I want you to realize that it's 2 separate coordinate points so you can make sure that you plot both points instead of accidentally only plotting one. Okay, so it's more for you than it is for me. Now I know that this was really long and a lot of information, but it is mostly review, and we are going to recap this as we go through the notes for day 2 and day 3. So if you have any questions, write them down on your paper and come in and ask me at the beginning of class tomorrow. Alright, I hope this was clear. See you in the morning.